In the previous lecture, we introduced the group theory to categorize the molecules. And in the next step, we are going to not only categorize the molecules itself, but also molecular orbitals are categorized by using the group theory. So as I mentioned, group theory was applied for molecules in a previous lecture, right? To understand the symmetry of molecules, but in this lecture, it is extended for molecular orbitals too. Okay. So let's take an example of the SO2 case. So SO2 is the similar type of the molecular symmetry as water, right? Which is categorized into the C2V, meaning it has symmetric operations of E and C2 and 2 sigma V. So which could be shown here. So S and 2O, O are indicated as A and B. Right? So this molecules is in a sheet. Oh, let's check that. So molecular axis is here, and then the parallel to this molecular axis, you have one sigma B, and also some sigma B dash mirror operation for this molecule. Okay. And now we are going to think about p orbitals of each of the S and the 2 O's, right? So px orbitals in here. So px meaning that in this figure, that we just take the x direction, like this. So px, right? And the 3p orbitals are going to mix and make a molecular orbital of SO2. Okay. And what we have to think about is that we have to check the symmetric operations for these molecular orbitals made of PS, PA, and a PB. Right? So let's think about this. So just by applying the sigma V operation, which is check. Yes. So let's make this. So this one actually taken differently. So this one sigma B dash. This one sigma B. So sigma B is in the center plane in atom S, right? So in this case, the mirror operation of the p orbital is switched back by the P of A move to the B side, and the P of B move to the A side. But PS doesn't change, right? So what it means is the PS, PA, PB is changed by sigma V operation, the PS, PB, PA, right? So PA and the PB are flipped, right? So this could be expressed with matrix operation. So initially, the molecular orbitals were PS, PA, PB, and after sigma B operation, it's changed to the PS, PB, and PA. And for this conversion, using the matrix calculation, since the PA and the PB are switched, this region is 0, 1, 1, 0, right? But PS case, it doesn't change, so it just add 1, so the other part is 0. So PS is just shifted to PS, and the PS and the PA and the PB are switched. And like this, we are going to obtain these transformation matrix by applying the symmetric operation. Okay, and this original the molecular orbital, right? For as an initial setup is called a basis of molecular orbital. And then this matrix is called now the D of sigma B, okay? And please think about for other operations like E, C2, and sigma B dash to obtain these transformation matrix, okay? So please stop the video and then try to think about the operation, okay? And then also, please, I'd like to remind you that p orbital has a positive and negative sign. And then please think about this too. Okay. So let's check out. Now our first, always starting point is PS, PA, PB. And if you apply the E operation, it's not going to change, right? EB, PA, PB. So meaning that for E operation, this unit vector, unit vector, the matrix. So now the C2 operation. So let's think about C2 operation. C2 means the rotation in this molecular axis. And then it means A orbital move to B orbital and B is coming to this way. But keep in mind that the sign also flipped, right? So if you move this molecule rotation, it's going to like positive, negative orbital, right? And also if the S orbital, if this one rotated, this one also positive, negative orbital, right? So that's a reminder for you. So based on this, so initially and the case C2 operation, so PS, PA, PB is changing into minus PS and then minus PAB and minus PA, meaning that this one is minus 1, 0, 0, 0, 0, minus 1, minus 1, 0, 0, like this. And similarly, if you apply sigma B dash operation, it's originally PS, PA, PB is changing into the minus PS, minus PA, minus PB, PB, meaning that this one is going to -1, -1, -1, the other is 0. Like this. So now you could obtain the operation matrix